Now that we can initialize our neural network, we need to create a function that accepts a network and the input over here and performs the calculations necessary to build the outputs that should come out on this end. And for that matter, I need to tell you about something called the activation function. Notice that as it stands right now, we have two weight matrices right here, and then two bias vectors right here. And if we look at the second drawing I have, we are going to perform some matrix multiplications and vector additions from the left of the network to the next set of neurons, and then whatever comes out over here goes into the next step. And so in the end, we can see that if I use these W1, W2, B1 and B2 letters, what we are doing is we take the input of the network, let's call it just I, and then we do W1 times I plus B1, and then all of this, we multiply this with W2, and then we sum B2. And I went ahead and parenthesized this because in matrix multiplication, multiplying on the left or on the right is not the same thing, and we actually want to multiply all the matrices on the left, so that's why W2 is over here. But as it turns out, I can expand this, so I can distribute the multiplication by W2 over the W1 times the input and over B1. And if we do the maths, this is equivalent to multiplying some matrix W with the input and then summing some other vector. And what this means is, or the repercussions of this fact is that no matter how deep I make my network, there is, regardless of the number of layers I introduce, and here's one, here's two, here's three, currently I only have three, regardless of the number of layers I introduce, if I just do matrix multiplication and vector addition, I might as well just have a single layer, because it's equivalent in practice. And that's not the point, because linear functions are useful, but they aren't as powerful. They aren't powerful enough. And so in order to make this more effective, and again there's research papers on this, so I'm just gonna go ahead and give a very, very intuitive explanation. In order to make this work, what we do is we make the first multiplication. Actually, let me draw something instead of write something. So we do this first multiplication, we get some vector that comes out over here, and then what we do is we take this black box called an activation function. So we call this an activation function, so that this comes in and we change it a little bit in a non-linear way. That's why usually you see the term non-linearity associated with the activation function, because this activation function is not linear, and so these 6 numbers go in and then 6 other numbers come out. Oops, that's not what I wanted. Slightly different numbers, but 6 numbers come out over here, and they are slightly modified in a way that when we give this to the next layer, so when we perform the next matrix multiplication and the next vector addition, those two don't cancel each other out. And by cancel each other out, I mean they are no longer equivalent to a single matrix multiplication. And so basically we just have to find an activation function that is suitable for us and insert it after this step over here and after this step over here. And there's a couple of popular alternatives. One, well, some of them have a more intuitive reasoning as to whether they should be used or not in certain situations. Some of them can be more easily interpreted. We are going with a activation function that is fairly simple to understand, even though it's not as easy to explain why it works. But let me just show you the one that is fairly easy to intuitively reason about. So I'm expanding this drawing over here. Okay. So let me draw two axes. So I'm going to make a plot right here. And in case you're not familiar with plots, this is just a concise way of representing numbers in 2 dimensions. And what I mean is, so I'm about to draw a very popular activation function, and the x-axis represents the things that go in the activation function, and this represents the things that go out the activation function. Out. Okay. And now let me draw two guidelines, very thin guidelines, because this activation function has a really interesting property, which is, so this is 0, this is the origin of the plot, this is 1, and this is -1. And the activation function looks something like, let's see if I can make this drawing, something like this. Wait, it's like slightly more slanted, something like this. Okay, and this is the sigmoid function, the sigmoid activation function. And the interpretation for it is the things that come in over here, so the numbers that come in represent the aggregated vote of the previous neurons, so whatever the previous neuron said, and then the sigmoid function, what it does is turns this into a binary response, as in 1 means I really agree with what the neuron said, and -1 means I do not agree with what the previous neuron said. For example, in our cat and dog case, for the dog neuron, if whatever goes in is over here, so a very big number, for example 5, then the previous neuron, what it means is the previous neurons altogether think this is a dog, and so we go right ahead over here and find the sigmoid function here, and this is now very close to 1. So what this neuron says is, yeah, okay, I think this is very likely to be a dog. Another example, if the previous neurons have an aggregated score of, say, -3, then we go ahead and look for the sigmoid function down here and find it over here. And this is a negative value, but it's not as close to -1 as this one was to 1. So we think, okay, this is probably not a dog, but our confidence is not very, very high. So that's more or less the intuition behind the sigmoid function. Just go ahead and Google it. Even the Wikipedia page can give you some more insight. And in our particular case, we are going to use the Leaky ReLU activation function. ReLU, so Leaky ReLU, written like this, as in rectified linear unit. And its plot is very, very simple, and it's very simple to implement, and it is what we will be doing next. So the plot looks like this. This is just the standard plot. And then the Leaky ReLU, I keep forgetting how this works. So the Leaky ReLU on the right half looks like this. So this is a line with slope 1. So this is slope 1. And on the left, it's still a line, a straight line, but it's very close to the axis. So this does not have slope 1. Over here it has slope alpha. And this alpha is a parameter that we can control, and it should be smaller than 1. And this is the function we are going to write. We are going to write a function that takes numbers in, and then the positive numbers, the numbers that are on this half of the axis, are left untouched. That's basically what it means to have this line over here with slope 1. It means that a number that goes in here comes out exactly the same in here. And for negative numbers, that is numbers that go in on the left side of this axis, those are going to get multiplied by a small number alpha to make them quote-unquote less negative. So if a minus 5 comes in, this is a 5 even though it doesn't look like one. So if the minus 5 comes in, we bump into the function right here, and maybe this was a minus 0.5. So negative numbers become slightly less negative. And that's what we will be doing.